So without further ado, we'll start with Michael Monagan.
Good morning, everyone from Vancouver. It's morning here still. I'm going to speak on this topic, mathematical experiments for mathematics majors. Let me move this out of the way. I've been teaching this course, MACM 204, for over 10 years, computing with calculus with Maple. The way we teach the course is we have 1 hour of lecture and 1 lab hour each week, so 2 hours. And the prerequisites are integral calculus in the first programming course. And the goals of the course are listed here. We want the students to practice their programming skills on math problems, not computing problems. So about a half the time of the course is programming with math problems. We do a review of calculus and apply it to realistic problems. We're using Maple's visualization tools. And the fourth point is the one I'm focusing on in my talk, learning to do mathematical experiments. This I've been working on recently. Another goal is to master the software package, that's Maple, for use in other courses. And at the end of the course, we switch to doing differential equations. And we get to modeling systems of ODEs. And I've been using the SIR model. It's the virus model, the basic virus model because of COVID as an experiment. So when I designed the course this semester, I'm teaching it right now, I have 6 assignments and I have 1 mathematical experiment per assignment. And here is the first experiment. The idea is to use Maple to check a theorem. So I have a statement there, stated as a theorem. It says the integral from minus pi over 2 to pi over 2 of sine mx times cos nx is 0 for all non-negative integers m greater than 0 and n greater than 0. And what I want is for the students, when they see something like that and they realize, oh, I have a tool that can just check it, that this would be the first thing that they would do. They would just naturally use Maple in this case to check it. So I assign them this problem. It says the first part of the question is to use Maple to check the theorem, to check that it's true for enough values of m and n to convince ourselves that it's actually true. And so I'm thinking they'll write a little bit of Maple code like this. It's their first assignment, so I'm teaching them Maple for the first time. So it is a double for loop. I think that's complicated enough for the first assignment. And I'm simply using Maple's integration command for the choices of m and n. Oops, sorry. It's too sensitive. And it's printing out m and n and a whole bunch of zeros. And so that's checked the theorem. We've checked the theorem's true for enough values, so we believe it's true. I actually found this quite unsatisfactory because, yes, we've checked that the theorem's true, but we have no idea why it's true. Why is it true? Maple says it's true, but we don't know why. So in the last 2 years, I added a part B to the question, namely to get the students to graph some of the functions. So graph some choices. I'm suggesting 2 and 3 for m and 2 and 3 for n. And if they graph any of them, they'll see why the theorem is true, because they'll see positive and negative areas. And this negative area is going to cancel out with this positive area. Sorry. And this negative area is going to cancel out with this positive area. And I'm hoping the students will say something like the positive areas cancel out with the negative areas. But I looked through the solutions to the students, and some of them are very good. Some of them recognize that the function is an odd function. And this is the answer that one student wrote. He said the integral is 0 because sine x times cos nx simplifies to a sum of sine functions. If you simplify that using the combined function in Maple, you'll get a sum of sine functions which are odd. And he goes on to say the integral of an odd function over a symmetric interval is always 0. So that's an interesting answer, a very good answer. Another student said that, whoops, sine mx is odd and cos is an even function. So a product of an odd and an even function is an odd function. So some of the students knew about odd and even functions from Calc 2. So that's the first experiment. It's the first one I get them to do. And I'm going to show one more, and then I'll show you a list of my experiments. This is a more involved experiment. My first technical job was measuring the flow of a river. So this is supposed to be a cross-section of a river. And I have some data here. I have x coordinates where I actually measured the velocity. So this is 5 meters across the river. The velocity was 0.1 meters per second. I use a flow meter to get this data. And we take various measurements. So these are velocities in meters per second at the bottom. And we gather some data. So we have distances across the river. We measure the depth of the river. And we measure the average velocity at that depth. You actually have to put the flow meter 40% above the bottom of the river. So if you put the flow meter 40% above the bottom of the river at a point, that speed will be an estimate for the speed of the water in this column. So the problem is we gather some data like this, and we want to get an estimate for the flow of the river, the amount of water coming down the river from this data. And this is how I did it when I was actually doing it for my first job. We used the following method. We approximated the area of each section with a trapezoid. And to get the flow on that section, we multiplied the area by the average of the two velocities. So the flow on this section is the area of that trapezoid times 0.35, the average of the two velocities at each end. And that seemed sensible to me. And then one day later, so that we did this, and I actually had to write a program to do this. The company bought a new plotter, an HP plotter, and they wanted me to draw pictures of the river on a plotter. This picture is actually done in Maple. So that's what I did. And then later I discovered another method for calculating it. It's like a midpoint rule. So you have a data measurement, say here at 5 meters across. And in the normal midpoint rule, you would have a section from 0 to 5 meters. You'd take a measurement halfway along at 2.5 meters along. But we can't do that because we can't just go back into the river to do new data measurements. We have to use the data we've actually got. So the way to do the midpoint method is to take half the way from the left to the current, that's here, and half away from the current point to the next measurement, which is at 10 meters across, that's halfway, and then to have a rectangle and use that to approximate the area of the river there, and then use the measured value, 0.1 meters per second is the velocity. And so we have a second method for doing it, and the experiment for the students is to figure out which method is more accurate. And in order for them to do that experiment, they need to know the exact flow. And so there's a formula here, an integral, which I'm sorry, I've got the pointer is also set up. Let me see if I can fix that. Okay. The flow is the velocity at distance x across the river times the depth of the river, integrated from the left to the right of the river. So we can get the exact flow, and then the experiment is to figure out which is the best method. Now, you've seen both methods. So this is the trapezoidal method, and this is the midpoint method. Which one do you think is the best? Just looking at it. The thing about the midpoint one is it's actually missing pieces of the river, right? It's missing the left piece and it's missing the right piece over here. So it looks like the midpoint method might not be the best, but it turns out that it actually is. So the students are going to discover that with some data, that the midpoint method is the better method. So we were using, and I can't explain why it's the better method using this rectangle right here. There's more water on the right that's flowing faster than there is on the left that's flowing slower. So the average of these two values, 0.425, is actually an underestimate for the flow of the river on that section. It's biased. Okay, so I've got these experiments. So I've shown you two. These are the other experiments that I have. I have something called the prime number races. That's in a paper by Granville and Martin. I found that, and I found it's a very nice example. It's basically using the next prime command in Maple. Students have to learn a little bit about prime numbers. I have an experiment where I get them to generate random walks in the plane and see what they get. I have a visual for eigenvalues and eigenvectors. I have two simulations. One is simulating a 30-year mortgage. You pay every week some money to the bank, and the bank charges you daily interest. And we're comparing that process with the result of a differential equation to see how good the differential equation approximates the actual process. So the simulating payments of a mortgage and interest rates. And the last one is to try and simulate in the SIR virus model, to simulate, you've heard the expression herd immunity. How many people do you have to vaccinate before the virus will start dying out? And we can simulate that for fun. That's it. That's my talk. So that's what I'm doing. You're welcome to ask me questions.
I have a question, Michael, if I can jump in.
Yes, of course.
So your first example, the sine and cosine Omer noticed that if m equals n, there might be a problem. If you do the integrals, indefinite integrals, you'll get an answer that divides by m minus n and divides by m plus n. And so if m equals n, the indefinite integral looks like it's dividing by 0. So I wrote a paper with David Stoudemire and David Jeffrey, integrating with parameters in a way that you might find interesting. We use a Kahanian factor just to make sure we get integrals that are continuous with respect to the parameters. In your case, it's okay because when m equals n, if you specialize it first, you still get 0. It's okay. The specialization problem but an adventurous student would look at that and go, integral of sine mx cosine x that I'm dividing by 0, the integral has an m minus n. What's happening?
Rob, I think what you're saying is if we try and do the integral symbolically, we'll get a factor of m minus n in the denominator somewhere. Is that it?
Yes, that's exactly right.
Yeah. Okay, I'm specializing first.
Yes.
So I'm arguing that, let me argue that this is an odd function, this is an even function. The product is odd, therefore we must get 0.
Sure. The point I really want to make, though, is that a student that is adventurous might run into something that you didn't think about.
Right.
And you may have to be prepared to explain some of these other things. And I like that. I think that's a good thing about experiments. So congratulations on doing it. And I'm glad that you did that. I'll throw the link to this paper with David Stoudemire in the chat.
We have time for maybe one more question or two.
Well, I think Rob's point just now is just saying it's a nice one that they're trying to evaluate the integrals symbolically is maybe a natural way for many students to approach the problem, but as he said, it leads to problems. or at least other things that have to be done before it works out. Whereas the even and odd approach is, quite nice, but I find a lot of students don't think about that first. And I think that's a nice idea, showing where both ideas have merit, but and have value in different situations. But you have to be able to master both and decide which one to use and when to use it.
I think there's a temptation on the students to try and calculate, and I'm trying to get them to step back and actually graph things if they can, because the graphs will provide some insight, or hopefully provide some insight.
I agree.
All right, thanks, Mike. That was great. And I'll also add that these are problems that you just can't do by hand, and having some software to play with makes it more real, especially when you visualize it. All right, we will move on to Majeed. If you want to start sharing your screen. Ajay, I think you're muted.
Okay, so you can see my screen, right?
Yes, and we can hear you. Perfect.
And the screen is visible as well. Perfect. Okay. Good afternoon. I'm from Toronto, so that's why I'm saying because the first speaker was from Vancouver, so morning for him. So my name is Asya, and I am PhD candidate at OIZ, University of Toronto, and working under the supervision of my professor, Alexander Cavalcante. So today I will present the project that we are doing for my presentation is a pedagogical study of MapleLearn effect on mathematical thinking in introductory calculus. So we all know that the digital tools are reshaping how students experience and understand calculus, turning abstract concept into dynamic, interactive explorations. By moving beyond static equations and symbols, technology empowers learners to visualize functions, experiment with parameters, and uncover underlying patterns that define change and motion. This shift transforms calculus from a subject of procedural memorization into one of conceptual discovery, creativity, and real-world connection, preparing students not only to master mathematical ideas, but to think like innovators in a digital age. So digital tools like MapleLearn, GeoGebra, and Desmos have become essential in modern math education. They make it possible for students to visualize abstract ideas and interact with functions and equations dynamically. However, despite their popularity, there's still a research gap. Very few studies have explored how these tools actually shape mathematical thinking. Most studies look at usability or test performance, not how students' reasons or develop understanding while using them. Our work addressed that gap. We are shifting the focus from computation to conceptual understanding, encouraging students not just to calculate, but to explore, conjecture, and reflect. In this way, MapleLearn become more than a calculator. It becomes a thinking partner in learning calculus. So our research framework builds directly on a pilot study conducted last year, where we explore how students use MapleLearn in short guided activities within introductory calculus. That pilot helped us identify which features of MapleLearn, such as dynamic graphics, symbolic manipulation, and interactive visualization, seem to encourage students to think conceptually rather than procedurally. Building on those insights, this year focused on three main research objectives. First, we want to understand how MapleLearn specific features support mathematical thinking, how students use interactivity and visualization to construct understanding. Second, we are examining how these features interact with calculus content, both in traditional academic exercises and in applied contexts, where calculus concepts are used to model real-world problems. And third, we are exploring student experience and perception of how they feel about using MapleLearn as a learning tool and how it influences their confidence and engagement with mathematics. Together, these objectives help us to see MapleLearn as not just as a technology, but as a pedagogical instrument that mediates mathematical thinking. So our participants were first-year calculus students at a large university in Toronto. We choose this group because it represents students encountering calculus concepts for the first time in a formal post-secondary context. The study involved 3 carefully designed instructional activities, and each focused on a major calculus concept such as functions, derivatives, and integration. Each activity was created in MapleLearn to leverage its interactive and visual feature, encouraging exploration rather than simple calculation. For data collection, we used 3 complementary sources. First, we analyzed students' actual work within MapleLearn, their steps, reasoning, and visual manipulation. Second, we took observational notes during the session to capture behavior and discussions. And the third, we gathered post-activity surveys to understand students' perception and learning experience. Together, these methods provide how students interact with MapleLearn and how it shapes their mathematical thinking. So we use mathematical thinking as a framework for this study by Mason. It describes 3 fundamental processes that define mathematical thinking: specializing, conjecturing, and generalizing. So specializing means exploring meaning by looking at specific examples to uncover patterns or properties. For instance, students might adjust a parameter or test individual value in MapleLearn to see how outcomes change. This step helps ground abstract ideas in concrete experience. So conjecturing means that once the student notices relationship, they begin forming hypotheses. They test and refine their ideas, asking questions like, does this rule always hold? Or what if I change this variable? MapleLearn interactive features such as slider and live computation make this process immediate and visual. So finally, generalizing is when students move from specific examples to broader principles. They recognize patterns and express them using mathematical language or symbolic notation. This stage connects exploration with formal understanding. So together, these 3 processes capture the essence of mathematical thinking, not just doing math, but reasoning, exploring, and discovering through interaction and reflection. So these are the features. Sorry?
Keep going.
So-
I think somebody just was unmuted.
Okay, so these are the features of MapleLearn: interactivity, document sharing, math input, math operation, and visualization. These features that we use in our study. So you can see the different colors they indicate which feature document sharing on a screen, and math input and math operations. So here is a simple example that I consider to show that how MapleLearn is helpful to in establishing mathematical thinking in any mathematical situation or problem. So the basic and any case, the specializing, conjecturing, and generalizing, all the Maple features like mathematical input, operation, visualization, and slider, they are useful to to apply these 3 steps. So the problem that we consider is about inflation and time travel, and the idea behind it is because it's a very useful in everyday world. So another I like to share importance of this project, that we divide calculus into different domains, and in this project we especially focus on calculus in economics context. So this problem, we consider mathematical concept exponential function, and we define this into 3 categories of mathematical thinking, specializing, conjecturing, and generalization. And in the end, we propose a question which, based on these three, the students are able to do their own, and we give as a challenge problem. So to better understand students' learning experience, we use a mixed data collection approach, combining student work with MapleLearn, observation notes, and detailed questionnaires. So this allowed us to capture not just what students did, but also how they felt about using MapleLearn, their engagement focus, and perception of its usefulness. The questionnaire includes several open-ended questions, and these are 9 questions. For example, the students reflect on their first impression of using MapleLearn, whether it made activity more engaging. We also ask how they might collaborate with peers using tool and how they manage their focus during the activity. Students described the challenges they faced and identified which functionalities such as document creation, visualization, interactivity they found most useful for learning. Finally, they offered suggestions on how MapleLearn could improve. These reflections provided rich qualitative data that help us evaluate how interactive tools can promote curiosity, conceptual understanding, and mathematical thinking within real-world contexts like inflation and purchasing power. So these are our findings. So for the user experience, students found MapleLearn visually appealing and easy to use, though some noted a slight learning curve. Engagement, in the case of engagement and interactivity, the hands-on features made math more enjoyable and helped students visualize abstract ideas. In the case of collaboration, the learner saw potential for teamwork, but wanted better real-time editing options as well. So the focus of the fourth point to understand like the focus. So the students saying that MapleLearn helped stay engaged once they got familiar with the interface. And finally, the features of interest, the visualization, interactivity, and document sharing stood out as the most useful. Overall, students viewed MapleLearn as an engaging and effective tool that supports deeper conceptual understanding. So pedagogical implications of Maple enhance visualization and exploring learning by allowing students to interact with mathematical concepts and move from examples to generalizations. It promotes engagement and deeper conceptual thinking through interactive exploration. However, some barrier remains, particularly in developing tool literacy and enabling effective collaborative use. In the future, so this we done with one university, but in the future we are in a collaboration to another university in Ontario. Almost we are done now. We are waiting for our ethical approvals and all those some paperwork, and we will perform the same activities with this group and see that how this can be we can better understand in pedagogical way, like the Maple incorporation in a classroom learning calculus under the framework of mathematical thinking. So in the end, I would like to say the thanks to Karishma, Paulina, and the content team. This work cannot be done without this invaluable support. Thank you.
Thank you. We can open the floor to questions.
Again, I have a question or a comment.
Go ahead.
Yes.
I enjoyed your talk. I see that. That was very interesting. Of course, the paper is very good too. I have a comment about studying students studying calculus. There was a paper of Uri Treisman's from many years ago, which had this kind of survey question that you have in here. And the students would answer the way they thought the instructor wanted to hear. And so Uri Treisman wired the desks. So he overheard their private conversations. and the results were very different. So it's probably illegal. You probably have to get ethics approval to do this kind of study now. But if you're interested, I will dig out that paper by Uri Treisman. I think it was called Studying Students Studying Calculus, and it appeared in the monthly some time ago. And so it's just something to keep in mind for future work.
Yeah, I appreciate if you can share that work with me. Thank you.
There's one question in the chat about the level of the topics that the students were looking at. Were the topics all what might be called pre-calculus?
Yeah, that's a really good question. We started from exponential function, that's part of the pre-calculus, but in derivative and integration, we are moving to advanced. So the exponential, because this project is based on 3 activities. So the plan was like to start from the basics. So in this way, the students can get better understanding of platform, and also how they can use and look the maths. And also the framework is like mathematical thinking, conjecture, specialization, and generalization. But the derivative and the integration, they are mostly for not like the pre-calculus, but as a first-year calculus.
Okay, thank you. We should keep to the timelines, and we'll move on to the next presenter, William Bauldry.
Well, greetings, everyone. I want to start by thanking the organizers for the opportunity, and also thanking Paul and Aram for keeping people who like to talk running along. It's a difficult job. I've done it before myself. And what I'm looking at is an Enigma M3 simulator. This is a little creature that was we'll just jump past that. This little creature that was built just before World War II and adopted by the Germans for German military, for coding, for messaging. It was the subject of a delightful movie about Alan Turing and his group, starring, I believe it was Benedict Cumberbatch. But the real thing that's going on here is I'm continuing a theme of things that you can build using components in Maple that make it easy for students to do a task. That's really what this is. So there is an Enigma. And the initial ones, they were something. They weighed about 50 kilos, and they weren't going to be wandering around in the field very much. Then they started, let's see, it was in 38, I believe. Yeah, there it is, 38. The Wehrmacht added a couple rotors to it. It's a rotor-based cryptology machine. And then they put a plug board to do some more transpositions. This made a machine that was thought to be unbreakable at the time. And it cost a little under $10,000 in today's money. That's not too bad. Enigma was not actually the name, or it was a brand name that Scherbius had come up with. He sold these commercially before. So let's take a look at how the thing worked. You pressed a key on it, and that went through this plug board where we have transposition of letters. The entry disk is really just an interface between a wire and a pin on the rotors. Then the rotor does a transposition. The next rotor does a transposition. The third rotor does yet another transposition. There's a reflection, and then back through the rotors. Now, when the key is pressed, before anything happens, the rotors rotate to change the transpositions. The right rotor is the quick one. That rotates with every key press. The center rotor every 26 press, and the left rotor every 26 squared press. The reflector makes it so it's a symmetric operation, and that way you can decode by having the same settings and press the encoding key. So as an example, suppose we're set up this way. We've chosen rotor 5 on the left, rotor 3 in the center, rotor 4 on the right, and then set them at the first notch for the left, the second notch for the center, the third notch for the right, and then the letter showing, the initial letter, an F for the left, a D for the center, and an A for the right before the key pressed. Press the Q key, that right rotor will change to where the B is showing. The plug board changed the Q to an A, then the right rotor an A to a C, the C to an H in the center, the H to an I in the left. The reflector did an I to a P, and then back through the left rotor a P to the D, the center rotor a D to the A, the right rotor an A to the G, and the plug board left the G alone. The lamp for the G lights up. It took two people. One was typing, the other was recording the lamps lighting up. Now, the fun part with the class is giving them a message and letting them crack it. So we're going to take the components, and this is the palette from the components. You can see a bunch of stuff here. There's a button, a combo box, sliders, check boxes, radio buttons, text, labels, just all kinds of things you can put in, gauges. By using these, we can build applications for the students where they can focus completely on the topic at hand and not learning syntax or whatever. It's a little different direction to go. So I have a cryptology package from a cryptology class that I taught, and this Enigma M3 simulator is part of that now. So we'll go ahead and get it in. Now we're in Maple, and we click on the simulator. We've got that. Maple workbooks let you put in documents, data, links, whatever. It's a wonderful little creature. For instance, here we have a hyperlink to Arthur Scherbius, and we can check him out just from Maple, jumping right to the Wikipedia article. So let's see. Definitions. Laurent had talked about putting documentation inside of Maple. This is all just straight text. There's nothing here. Then here we'll get to the simulator. So we have a button. It says initialize. I'll click it. And we've now initialized. The students haven't had to do anything yet. We have to choose which rotor we want out of the set of 5 for the left rotor. So we have a pop-up that says, oh, which one? Look, let's go for 3. And the center, well, 3 is no longer available. We use that, so let's go to 2. And on the right, 2 and 3 aren't available. Let's go ahead and go to 5. And then our ring position, 1 is good. Maybe 10 would be nice, or maybe 3. And then the letter showing, how about V and maybe Z, and this one at B. The plug board for transpositions, let's swap H and Q, and let's swap E and P. That's enough. Now, typically what happened was an officer would select the 3 rotors, put them in, he would set the ring positions, close it up, then the operator would adjust which letter was showing and the plug board. And that would be the setup. Down here we have an Enigma. And there you can see that the V, the Z, the B are the letters showing. Here are our lights. Here's our keyboard, and then the plug board down below. We mapped Q to an H, I believe, and P to an E. Those are invertible, of course. You see the double plug, and that's why we had 2 wires, 1 for each direction. So let's send a message. H, the Q lit up, E, the M lit up, L, the V. Press L again. Now it's Q because that rotor stepped, so we get a different one, and O. Notice that the letter up had advanced each time. Then we can go down here instead of having someone stand by, here we have our plain text, the hello, and the ciphertext that came out, QMVQC. We can look at the different encryption steps that went along inside the machine. This is helping students to understand how the transpositions were connected and work together. And we could look back at some of the previous, the H at the beginning. Let's see, where is that? I guess, here we go. Let's look at the L. And it came out as the Q. Now, what happened in practice was there were code books that each entity had. And let's read some code book. We'll pick a year and a month. And what day should we have? How about the 5th of August? These were the settings for that day. And just because it's much simpler to do this, we'll, instead of trying to copy that all up, we'll insert the settings. Come back here. There they are. The 4th rotor goes in left, the 3rd in center, the 2nd in right. 26, 22, 25 were the ring settings, then the letter up. And they, in practice, they did always 10 transpositions with the plug board. We'll set up the Enigma and we're ready to go. Plug board's a little messy now, but we'll live through that. Let's say hello again. Now we have B, O, J, J, and O comes as a Q now. We can, so our hello came out as BOJWQ. If we'd like to look at a real one, well, it's a Maple workbook. We can embed items. So here is the sheet for August 1939. The day started, the bottom started at 1, going up to 31. That was so they could tear off a strip. The officer could tear that off, hand it to the operator, and work his way up through the month. These are the rotors chosen. These are the ring settings. Always 10. This was a flaw in the operation, and that helped crack it. Always 10 transpositions, and then initial letters up settings. Notice that this is actually a JPEG, but it just popped up as a Maple page. If you'd rather, instead of using one of those, since there aren't many of them available, we can choose a month, say January, and a year, say 1939, and just generate a random code book. What happened in the background was a little bit of code, and over here on my desktop is now a code book with random settings put in. This way we can have students play around quite a bit instead of being stuck in those 3. Or if you really want to get at them, now I'm not sure if this will come through Zoom, so you'll have to let me know.
And unfortunately, no.
Okay, what that was a short transmission in Morse code, which is what they did. And the Maple, one of the components is a speaker, can just drop that in. The code transmission was sent to the speaker, and the received code was actually these 4 letters, or excuse me, these 2 blocks. RGYUE and LNVUK. And if we knew the settings, we could then figure out what that was with a little bit of work. That's what Turing's bombs did. The name bomb came from Marian Rejewski in Poland. They called it a bomba when they built their machine first. Here is, and again, this is embedded in the Maple workbook, a message. Let's make that a little bit bigger. Now, Maple passed this one off. This is a PDF, And so far, Maple doesn't display PDFs, but Laurent gives me hope that this is coming soon. This is an actual transcription of a German message that was sent in Morse code. It begins with a bit of the call letters of the station sending it and a checksum, the number of characters, and that's how you can identify that this copy has an error. The checksum's 203. We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. 5 rows of 8 groups of 5 letters, but one of the groups is missing. And if you look up here, ZCDZ, that's missing a letter. So either one was dropped or, yep, some transcription error in there. That would have been a problem when they were trying to decode it. And then, of course, you can embed other resources in there. We have websites all over the place. Paper Enigma is actually another little PDF buried into the Maple workbook. And you can make one out of paper and have students work with that. So you don't have to spend, the last I knew that what an Enigma was auctioned off, I think it was about $150,000. So they're a little on the expensive side to buy for a class. Then other documents and whatever. And the last thing is every year there is a cryptographic challenge. This is the Maritime Radio Historical Society. And what they do is there's an Enigma. Every year they do a transmission. Here's the code sheet for the one they did this year. You have to get yourself an HF radio and listen to it. They do transmit the Morse code and capture that, and then it's figure out what it was. So it's quite an event each year, and they send out certificates. And my clock is telling me wrap it up. So we will look here. This is where you get started, the online help for embedded components, and that gets you working with these creatures.
Thank you, Bill. That was excellent. There are a couple of questions in the chat. One is just about the structure of your workbook. Where do you put your code? Do you put it behind the buttons, or do you put it separately in a module?
So
or what?
Here we are at the initialize button and edit the click code. This is the code to initialize the system, and it's all with that button. However, on one of the other parts, the cryptology, in this overall workbook, it has a text file that is code. It's because it's much easier to edit. And so in there, I read in the text file. Let's see if we can pop that up quickly. Hello. That's not quick. That's still not quick. There we go. So here you see cryptolib v 2.6 source.txt, and it's a text file embedded in the workbook, and that's just read in, and that defines all of the pieces for the library.
But for those who aren't familiar with workbooks, can you show the workbook palette?
Here we are.
Right, so there's 4 attachments there, or there's many attachments, I guess.
There's many attachments. For instance, I have in the cryptology package, there's the Playfair code, and that takes words as keywords to make the code. And so here's a small text file that came out of pulling most of the small words out of the Unix dictionary. It's 3,300 words, and that just lives inside. Or here we have, let's see, here's the recording. Oh, nope, that's not the recording. Here's the recording. Maybe we can play the WAV file and get that. Apparently not.
One more question in the chat. Is your crypto lib available for people to access somehow?
Aha. If we go back, excuse me, go back. And there's the crypto lib. There are 20 routines in it right now, plus some cryptanalysis. And why, yes, there are QR codes to get to it, or you can send me an email and I can send the link to you.
Okay, and they're available on the Maple Cloud.
Yep, Maple Cloud is a wonderful place to distribute files.
Excellent. That was great. We wish we could keep going, but we'll have to move on to the next presenter, as always. Next is Willem Andriessen.
Okay. Well, let me start. Okay. My name is Willem Andriessen. I'm a lecturer of Han University in the Netherlands, in Arnhem, Nijmegen. I want to talk about control engineering given to my students some time ago. And I used Maple 2022 and MATLAB Simulink 2022. And one of the goals of my talk is to let you see which platform is the best for educational purposes. So I have 5 items I want to show you. So let's start quickly with pole placement for servo systems with integral control. Okay, before I tell you what it is and why it is for, and let us go to a block diagram of a control system in state space matrices, the input matrix, the output matrix, the system matrix, and then state variable feedback control, where we feed back the states x through a constant k, a row factor indeed, to the input. So we have a control system here. And the challenge is to find a k where let me see an example of a phase variable form to make a controller for that, a state variable feedback controller with a input multiplier to get a system that has a 0 steady state error after a let me say a unit step input. So we have solutions in the frequency domain and we have solution in the time domain. And let us look at the solutions in the frequency domain. So excuse me that I do not explain all the formulas and expressions we use, but that's we don't have too much time to cover that. So we want to make a control system that that satisfies certain requirements. There are 2 control requirements, very important: overshoot in the unit step response and settling time. For instance, 9.5% and 0.74 seconds. And using these control requirements, we can generate 2 second order dominant poles that will satisfy these control requirements. And one manner to do that is to use this formula found in the book of NICE, Control Systems Engineering, or even better, using the real part and the imaginary part of the pole using these two formulas. And because we have a third order system, as you can see, we use a third pole, and we can take the pole at minus s is minus 5, because there is a 0 also in s is minus 5. But the suggestion of NICE is, don't do that. Set the pole at minus 5.1 and see what happens. So let us see what happens if we start the simulation. These are the control requirements. This is the real part. Here we find the imaginary part. And because the control requirements are in 2 decimals accuracy, we round them up also to 2 decimals accuracy. And the third pole is set at minus 5.1. So then you get a system where the denominator of the transfer function, also called characteristic equation, required characteristic equation, is given here. And now the problem is to find k, and for that we construct the actual characteristic equation from this expression of the state space matrices, where AC is the system matrix of the control system. And that was, we go back a little bit to the A and K together in one block diagram will be AC is A minus B times key, what here is given. And of course we have a nice derivation how we go to this transfer function, but there's no time to do that, so we go back to our example. So we find our actual characteristic equation using this formula, or from the denominator of the transfer function. And now it's safe to find the case by equating equalize components of S with each other into 3 equations, like here, and solve these equations and find them very accurate in this row vector. And now we can compute the closed loop system matrix and also find the closed loop transfer function of our control system. And now we use a input multiplier to gain a so-called zero steady state error expression, unit step response. There is no steady state error because the value is 1, and it's even by amplitude the height of a unit step, so to speak. So now we can also check if we have gained the control requirements, like the percent overshoot, and it's 10.1, it's very good, and the 2% settling time is also within the limits, okay, because achieved was 0.94 and achieved was 0.67, so that's very good. However, if we had cancelled the pole, the 0 at s is minus 5, then the control requirements would even be better, as you can see. So the designs are both considered to be very successful. And my goal was also to let you see how MATLAB was doing that. And you can see how awful the output is. And it is only the code. It's no output. And there are also a lot of functions. We don't know what they really do, like Ackermann and place to find the decay, that we found by equating the two characteristic polynomials. That's also done here because you can do it also in MATLAB. But for educational purposes, MATLAB is far better because the output of MATLAB is all gathered at the end. And you have to figure out what is what. And there are also plots, they are really good with, like here, the overshoot 10.1 and the settling time. So the outcomes are best, but for educational purposes to say and to explain why things are computed the way they are, it is much better to do that with Maple. That's my point. Here I have also the complete Maple program. It's very large and you can execute it to see what happens. Now I come to the design of a state variable feedback controller with an integral X inserted in the loop. It's much better than using a multiplier at the input. So here we have the SVF controller with the AC, the closed loop system matrix. And here we have the integral control with an integrator inserted in the forward loop. And the expressions for state variable feedback plus integral control are given here and nicely found with this formulas. And there's no time to code them through, but the outcome is this. The state vector is extended with the integral state, and this is a so-called partitioned matrix or blocked matrix, and one of the blocks is, for example, A minus B times K, this dimension n by 1, and we have a submatrix B times Ki, and then the input matrix and the output matrix are also block matrices. So let us see what the challenge is of an SVF plus I controller. Is not only to find the feedback gains matrix, but also the integral feedback gain, Ki, and such that they are satisfying the control requirements. Okay, let's see what we can do. We take again an example from the textbook of Norman Nice, a little bit altered, but not too much. So we first design a state variable feedback controller without, and then with an integral controller. And you will see it can be done in MATLAB and also in Simulink. You also know that it's also a nice program to show, you see. But then you have to compare it with, not with Maple, but with MapleSim. That would be nice and fair to do. But let us first look to the Maple solution. We first have to find the so to speak, the required polynomial from these formulas. You can also pick a formula. And here you see the TS2 and the POS dictating P1 and P2, two dominant second order poles, which are rounded here, and find the required characteristic equation. And then you can design the controller by finding k, and then also computing the symbolic characteristic equations with the symbolics k1 and k2, and then equating likewise coefficients from s square and s to 0, and then we find the k being these two simple numbers. And what you then can see is making a transfer function, closed loop transfer function, which has not the right DC gain, so the response will not be 1 here. And a little bit time ago, we multiplied the input here with the opposite of this number, so it came to 1. And that was the method of finding an SVF, state variable feedback controller N. Okay. So the control requirements are really good for POS and TS2. That's satisfying, but the steady state error is far too large. You see, so that's not okay, and that's why we insert an integrator in the loop. That's what we are doing here. So here are again the state space matrices, and then we use the big formula to find the controller. And as you can see here, these blocked matrices in Maple are entered like this, and also the input vector and the output vector. And that was really not a problem doing so in the Maple, because multiplication of matrices is done with a dot or with a fat dot in between, and it's all very easy and explainable. Okay, so we have a new required polynomial and a new actual polynomial, which we can compare to each other and find the case. And the feedback constant and case are found by solving the equations, and we find a very large key I, because the steady state error was so big. We need a lot of effort to get rid of that. Okay, so we can also go through the states to find the output, but we don't do that. We use, as we have seen here, skip this. We use the closed loop transfer function instead of the states. So we look only at the transfer function, the closed loop CCW, and what we see here, it's exactly no steady state error. And the performance is very well. All the poles are at the left have a negative real part, as you can see. So the system is stable and there is no steady state error at all. And the settling time and overshoot are very good, because desired was mine less than 10% and obtained was 8.1. And also for the settling time, it was very good. But the control effort, and that may be a problem with this kind of controllers, is very good, very large in the beginning, as you can see. And it stays at 3 point, because the limit is 3.0. Looking at the MATLAB solution can also be done in MATLAB. Very straightforward. but MATLAB does not have a nice presentation problem within method within the program itself. And you have to put the outcome of the program in between the program by hand, like this plot. And also here you see the plot with the settling time, very good, and also the overshoot a little bit different, not the same value as Maple has. That's a problem, maybe. And with the controller, you need to do something extra in MATLAB before you can do the same as in Maple, but the graphs are the same, as you can see. Also the control effort, very large in the beginning. And here is the complete Maple script. That's why how you can see it's not so nice as Maple. Don't you agree? It's seemingly awful, but it works. And I think for industry and government is maybe a good thing to have, but for education it's better to use Maple. This is quite simple what I show you today. And we also use a lot Simulink, but there you need so-called callbacks, and that's MATLAB. So it doesn't help very much.
So
And simulation results.
we're running up against time. I think
Yeah.
you're at the end anyway, but
It's
were
very
there any
technical,
final-
I suppose.
Are there any questions for Willem? I have one. Have you tried Maple Sim?
No,
Not yet.
not. I'm a retired teacher, and at that time it was we didn't have it at that time. We did only have Simulink. And I have also seen that Maple 2025 have more opportunities regarding control engineering, I think. Is that true?
I'd have to look back. We're always evolving the packages, so that's entirely possible. Yeah. We definitely beefed up the differential equations. Dynamic systems, I'm not sure, but possibly.
Yeah, so I was liked it very much to use Maple in that time, but most people use MATLAB for this kind of thing, for control engineering. But it's certainly a method and possible to use Maple for it.
Yeah, and
give more
in
insight.
industry as well. Yeah. All right, I'm going to have to cut it off there. Thank you for your presentation. That was
Yeah,
very
okay.
nice. Yeah.
Yeah,
The
thank you.
last presentation in this section is Daulet Nurahmetov. If you could stop sharing, Willem, we can move to the next presenter. Thank you.
Okay, thank you very much.
Hello everyone. Let me share my talk. In this talk, I will present how we use Maple for studying practical course in differential equation for master students in first year, in second semester. These master students are prepared by program math teacher for secondary school. And here main question we discuss what percentages of boundary value problem with second order non-homogeneous differential equation, and we firstly discuss some algorithm for construction what percent problems, and the second step we construct some exact examples for this algorithm. In last step, we check our results with Maple, and in Maple with dissolve comment, and compare our results. Okay, let me firstly formulate our main theorem, including work percent problems. This theorem formulate for partial differential equation in generally for work percent problems in the paper 1-2. We adapted this theorem for our problems. In our case, we consider first equation, second order non-homogeneous equation. Here P1 and P2 in some constants, and we consider in some internal boundary condition. Here we have some integral additional condition. In this case, we have all work percent problems, and second part of this theorem, we have some non-homogeneous equation 1, and we have some additional condition for right hand side f of x everywhere, including L2 space, and we have some unique solution y of x, and where we y of x satisfies a priori estimate. Then there is a unique set of function is boundary function sigma nu of x from L2, and such that we additional condition equivalent our internal condition 2. Okay, let me show one theorem with respect to Cauchy problem. If you consider Cauchy problem for equation 1 and with initial condition 3, then solution of this problem given by formula 4. Here k of xt is a Cauchy function, kernel of this integral, and we can construct this function exactly by next formula. Here y1 and y2 independent solution of our equation 1. In the case f of x is equal to 0. And okay, next step we consider equation 1, and we perturbate our initial condition for in the form y0 is equal to h0, y prime 0 is equal to h prime 0. Here h of x some arbitrary sufficiently smooth function, and we can calculate values of h of 0 and the first derivatives at the point 0. Then we have Cauchy problem, and we can calculate this solution of this problem by formula 5. And we can present one example for this problem. Okay, in our case, h0 is equal to 0.2, and prime of first derivative of h is equal to 0. And in this case, we have p1 and the p2 is equal to 0. F of x is equal to 1. we consider this equation at the interval 0, 1, and we have unique solution in this case, x squared divided by 2 plus 1 over 5. And we want to present how we can use Ötelbaev's theorem, first theorem, in generation well-positioned problems using of boundary function sigma 1x and the sigma 2x. Okay, if you choose sigma 1 of x from L2 space 0.4x and sigma 2x is equal to 0, we have 2-point boundary value problems generated from our condition 2, from this condition, and the corresponding Ötelbaev's theorem, this problem has unique solution, and we can calculate exact solution of this problem. Okay, next step, we can check our results using of Maple, and this so we formulate our ordinary equation, differential equation. We put all our coefficient of the equation and put our conditions, and we can check our results. Okay, next step, we can consider 3-point problems analogically previous examples. In this case, we have also unique solution. We can also check our results using of Maple and compare with our analytical solution. Next step, we change our differential equation, and in the case P1 is equal to 0, P2 is equal to 4, and in this case we have unique solution in this form. Also, we presented differential equation same as previous examples, but we have internal boundary condition. It means we have some non-local condition. In our case, this corresponding some initial condition perturbated by integral condition, integral term. In differential equation, it is called internal because we take all values from interval 0, 1 by integral. We can also firstly find general solution of our equation, and we find particular solution using of these internal two conditions, and we have unique solution in this form. How we can check our results with Maple? Firstly, we find a general solution of our equation, and we using our internal conditions, and we can calculate as a system of linear equation, and we find C1, C2 constant from our general solution and substitute to our general solution. In this case, we have also unique solution in this form. Thank you for your attention. If you have any question, I can answer. Can I add also one moment? Here we also generate these results for 2-point problem, transmission problem. In the case we have some additional condition at the middle point from 0, 1. For example, we have some additional 2 condition at the point 1/2. This result published in the in this paper.
All right, thank you. That was excellent. Always enjoy a talk on differential equations.